like what is immediate addressing mode, and what is direct addressing mode, and what is register indirect addressing modes, and then how to write the same program, that is like addition. So adding of 2 bytes, how it can be done, and so how to use the syntaxes, okay, writing your program and all we have seen. So now let us go ahead. We will be covering the other addressing modes, the addressing modes which I given you the list, that is of 10 to 12 in row. So we covered only 3. Let us cover the rest of the addressing modes. So before going, let us recapitulate what we did. So the addressing modes is nothing but the way of locating data in the instruction. So when you write any program, your instruction has to get the data or the operand. So how you specify your operand in the instruction, so that the processor, when it is decoding the instruction, on which data it will work, is what we are going to see in this addressing mode. So let me share my desktop. Yeah, so coming to the addressing modes, last class we common the contents of 2000. So here the memory, so your source, so this is what your instruction format. So this is your opcode. Move AX is an opcode, and then the operand is specified in the memory. So the source is memory here, and the destination is a register, right? So then in the last class we have seen how to calculate the address. So the address, which is of 20-bit, but here it is of 16-bit address is what it is shown. So calculation of the address would be ds multiplied by 16, that is 10h, plus this offset has to be added to that. That is the 20-bit memory address from where the processor will fetch the operand is specified by this memory location. So this is what an example we have seen. So move AX comma in 7000. So that's our 7000. If DS is 1000 and 7000 when you add, then the address will be 17000. And from that memory location, now if you see 1700, the content is 34, and 17001, the content is 12. So this 34 will be moved to AL, lower byte will be moved to AL, and then the higher byte will be moved to AH, is what we call it as a little Indian, right? So now we have seen the the limitation of the direct addressing mode. So here, when a memory location, see here, in this addressing mode, you have to specify the memory location in the instruction. So the direct addressing mode is useful for infrequent memory operations, right? But when a memory location must be read from or written to several times within a program, then the repeated fetching of 2 bytes of logical addresses make this mode inefficient. So the direct addressing mode has disadvantage of locking the memory addressing to the instructions, right? So then to overcome this, what we did is you can go for register indirect addressing mode. In the register indirect addressing mode, what you do is you will point out the memory location by using a register. Here you can use BX register as a pointer. Now if you see the example, move contents of BX, that means BX is showing a memory location, and that memory location, right, you move the content of CL into the memory location which is pointed out by using BX. So here we will use memory pointers. You can use BX register as a memory pointer. You can use SI or DI, source index and destination index registers, to point out the memory location as, right? So the effective address can be calculated like this. So if it is the instruction, this is what the memory is pointed out by using BX. So the BX content here is like, if it is 0300, that will be added to 1000. So then from that particular address, right? So this from that particular address, that means the memory address is 10300. So the content of register CL is moved to a memory address. But the difference is, in this addressing mode, we are not going to specify the memory addresses directly in the instruction. That is, indirectly is what we will mention is. Right? So this is what an example. Register indirect addressing mode. One more example, move DL comma the contents of SI. So SI is pointing out in a memory, and from that memory content is moved to DL. But that memory calculation would be your data segment register multiplied with 16 plus you can use BX or SI or DI or BP. So these are the memory pointers you can use in register indirect addressing mode. So that is the memory address, and from that memory address you copy the content, right? Here it is in a byte, or it can be a word also. So if it is move DX comma contents of SI, right? So this is what a register indirect addressing mode is. So now if you take an example, if you take your DS is 0800, right? So if you take DS 0800 and SI 200H, so then these two contents, so 0 will be appended here, then 0A00 is the address. So 0A00, if you have 1, 2, that content after when processor executes this instruction, move DL comma contents of SI, then this 1, 2 will be moved into DLS, right? So this is one example of your register indirect addressing mode. Now let us take the second example. Now, so your stack segment. So here in this case, if you see, even the moment you use stack segment, and the stack segment pointer is base pointer. So here the example, stack segment is 0800 and then base pointer is 2000. Then if this is the instruction, move contents of BP comma DL. So source is DL, right? So you move something into DL, that DL has to be moved to a memory location. So then what would be the effective address of the memory location is? So then you can simply work it out. Say similarly how we did. So 0800, and you can add 200 to that, and if the DL content is 7, that 7 will be moved to 0A000, same thing like, right? So here the segments can be overlapped, no, right? So what is that and all, we can see a little later. Then the next addressing mode is indexed addressing mode. So in this indexed addressing mode, what we do is the offset of the operand is stored in one of the index register. Right, DS and ES are the default segments for index registers. Right, so DS, to point out DS, we are going to use DS and ES. SI and DI is what we use. Right, and this mode is special case of the above discussed register. So this is anyhow, this is the same. So move AX comma SI, but in particular you are going to use the segments, default segments DS and ESS. So move AX comma SI is an example of index register. So SI, the memory is pointed out by using source index, and that memory location, just to it copies a word into AX, right? So the address will be calculated like this: 10H multiplied with DS plus to the contents, right? So this is what an example of indexed addressing mode. So now if you try to see the first example, move DI minus 8 comma BL. What do you mean by this? Now let us see. When the processor executes this instruction, the contents of BL will be moved to a memory location which is indexed by DI. So the calculation is this: DS multiplied with 16 and then the content of SI or DI plus any displacement. So here now you see, now if ds is 0200 and if di content here, if it is 0030 and the displacement is 8, so then the total effective address will be calculated like this: 0200, and when you multiply with 16, 0 will be appended here. The content of di is 0030, so 0030, and the displacement is 8. So this is what the advantage, right? So the content which is, that also you can use the displacement also you can use 8. So the effective the memory addresses, or we call it as the base address plus your pointer, that is what your effective address, or physical address is what we call. The physical address is 02028. So now if you see in the memory, if you have the memory and then 020028 is contained 17, then after, if BL is having 17, so then this 17 is going to a memory location of 02028. There, it moves the data. So here, what is this index addressing mode means? You can use SI or DI for pointing out the memory, and you can use in this index addressing mode a displacement 2, here in this example as 8, and that is how you can calculate the total memory address, right? So this is what of one example. Next addressing mode, so this is indexed addressing mode. See, it is like learning grammar. Addressing modes, when we see, without knowing grammar you cannot form a sentence. Similarly, when you are going to write your program, you have to know the addressing mode, right? So how you locate the data, or like, if this is the instruction, the content of BL, where it goes, so then the memory location is pointed out by using this index register. That is what we call it as indexed register or addressing mode. So the next addressing mode is based addressing mode. In this base addressing mode, the simple difference is you can use BX register or BP, base pointer register. You can use BX register or base pointer register for pointing out the memory. That is the difference. In index addressing mode, you are using SI or DI, right? So then what is the difference between register in the addressing mode and based addressing mode is what means spin. So here BX appears in the instruction operand field, and segment registers DS is used in this address calculation. That is what you have to know very particularly. And if BP appears in the instruction operand field, then the segment register which you have to use is stack segment. Okay, right? So that is the difference. So BX means DS you use in based addressing mode, and if you have base pointer means you have to use stack segment, right? So now this is an example. If the instruction is move AX comma BX plus 4, then that means you want to copy from somewhere memory and that memory content into AX. Then how it works and all. Now let us see. If DS is 0100 and BX is 0600, you can do it with me, like how I am going ahead. You can write down and then you can calculate too. So here some memory content has to be moved into AX. It is an OD operation because we used here the destination AX, which is of 16-bit. So BS is multiplied. So here BX is a register. When it is BX is a register, you have to use DS. When BP, if it is in operand field, then use SS. right? Sometimes all the data will be given like DS, BS, to confuse you, right? So then you have to pick up the proper segment. So now if you try to see, this DS is 0100 and BX is, it is multiplied by 16, so it shifts 4-bit left shift, so 0100 and 0 will be appended on the right. So 0600, and then here you have a displacement of 4, right? You can specify, like, if you use a pointer, then you have to go for 4 times incrementing the pointer. But if you know exactly where is your data, then you can specify your displacement. That is the advantage of this writing displacement in the instruction. So the displacement is 0004, and then the physical address is 01604. So now let us take, if you have 01604, the content is B0, and 01605, the content is C0, and after the processor executes this instruction, 16-bit data will be moved into AX. So the content of 4 is B0, so B0 will be moved to AL. So you have to be very careful, you have to use a little Indian syntax for Intel processors. So here you have B0, so the B0 will be copied to AL and C0 will be copied to AH. So this is what an example of base addressing mode. Similarly, you can try this example. If the instruction is move BP -7, CH, that means move the content of CH to a memory location somewhere. So here CH is it is an 8-bit. If CH is having a data of AB, which is an hexadecimal, then if stack segment is 0A00 and then BP is 0012, then what would be the content of CH will be moved where? So here now you can take this as 0A00, and this stack segment is multiplied by 16, which is nothing but 4 left shifts, and then the contents of BP is 0, 0, 1, 2, right? And the displacement is 7, right? So the displacement, this is minus, it is not going to be added, right? So this is 2, 1, 0, A, 0. And the displacement is, see, this is 1, 2. So 0, A, 0, 1, 2. When you are adding, the next is 3, the next is 4, next is 5. So like that 7 you have to add, but here this is not adding, right? So you are BP -7. So the moment it is BP -7, so then what you can do is, so 1, 2, this is 1, then it is 0, A, 7 less, 0, A, 0, 1, 1, then 1, 0, right, 1, 0, and then you can think of now. This is 1, 0, right, and then what would be the next? Right, so here it could be 0, F, that means 0, A, 0, 0, F, and next is E, next is D, next is C, same address. So now 7 less, right? So 1, 2, 3, 4, 5, 6, 7. 7 is B. So the address is 0A 0 0 B. So that content will be moved to, that means the content of CH. So if it is in a memory location pointed out by using this effective physical address, then the content of CH is AB, and this AB is going to be moved here. All right? Yeah? And now, so this is what base addressing mode. Is it all right? And the next is base plus index addressing mode. Effective address of the data is formed in this addressing mode by adding the content of base register, that means any one of BX or VP, to the content of an index register. So it is base plus index. See how you are locating the data or the operand in the instruction. So now if you try to see, move AX comma BX SI, then the memory location, so from memory location you are going to move 16-bit data into X. So then the effective address will be calculated like 10, that means DS is multiplied by 16 plus the content of BX plus the content of SI. So that particular operand, the memory location content is going to be moved into AXs. It is base plus index, both registers, base registers like BX or BP and index register like SI and DI, the contents are going to be moved into AXs. Right? So the destination is provided partly in the base register or BP and partly in index register, and there some provides the effective address. So now this is what this is how you calculate the total physical addresses. So based index addressing mode, this is an example, right? So data segment register or stack segment register based on BX or BP, and then the contents would be SI or DI. This is how you calculate your memory addresses. Example, if the instruction is move BP SI comma AH, the content of AH has to be moved to a memory location, then the effective memory location can be calculated like BP is there, then you have to consider SS, and SI content is this, right? So then this BP and SI are going to be added, then the effective address is 24800. See, in the first class we have seen like 8086 has 20 address lines, and the effective address is of 20-bit, and the lowest memory location is 0000 and up to FFFFF. So this memory location is in somewhere in between, right? So now the content of AH, if it is 7, then that content will be moved to a memory location 24800 is. And you can try the same example, a problem, you can take down this problem, like, if an instruction is move BX plus DI, comma CH. So the moment it is BX, you have to use DS, and DI content you add, and then physical address is what you can calculate this. So now the next addressing mode is based indexed with displacement. Based index with displacement. Now here if you see, you have base register, the index register with a displacement. So here the displacement you see 2080, which is a 16-bit displacement. Also you can go ahead with. From that content also it can copy the data. Right? Yeah, this is what the calculation, the syntax. ds multiplied with the bx, ds multiplied with 16, content has to be added to si, bx plus si plus the displacement is. Now this is an example based indexed with the displacement addressing mode. If you now try to see move cl comma, that means you have a memory location and that memory location content has to be moved into cl. Okay, so now if you see this example, go through once how you calculate. So after the processor executes this instruction, the content of CL20 will be moved to CL, but the 20 is a 06090. Is it all right? Yeah. So then you can try with this example. Your SS is 1100, BP is 0110, SI is 000A, and CH is, if you have AB, this is a 16-bit data. Then after execution of this particular instruction, the content of CHAB has been moved to a memory location, which is pointed out by using this. So this is based indexed with displacement addressing. This is how you locate the operand. Okay. Then next one is a register relative addressing mode. It moves a byte or word between a register and a memory location addressed by index or base register plus displacement. It is same, register relative addressing mode. Relative we are calling because here you are using memory pointer with some displacement. And move ax comma array of bx. So this instruction you are going to use when you try to do this programming in assemblers. Right. So you are writing your program in an emulator or an assembler like MASM. Then you can use this array kind of thing. But when you are executing this in your lab, I don't think so. If you are doing it in MASM or emulator, you can use this syntax array of bx. Array can be a variable which is having a particular addresses. So it is a memory location in array. So now this is what an example of register relative addressing mode. From a memory location of 10304, then it will be moved to CL. So this is register relative addressing mode, right? Then base relative plus index addressing mode. Base relative plus indexed addressing mode is what you can call it as. Examples are this. So what we discussed up to now, if the effective address calculation produces a value greater than 0FFFH, then the CPU ignores the overflow and the result wraps around back to 0. This was an important thing you can take, like if FFFF, if the value is greater than 0, then the CPU ignores the overflow and the result wraps around back to 0. For example, if BX contains 10, then the instruction move AL comma 0FFH, right? BX, this is what the displacement is. Then we load the value of AL register from the location DS, right, 0FH, not from the location DS1000F. Okay, is it all right? Yeah. Then this, I told you the MASM, you can try this. MASM stands for Microsoft Macro Assembler, and you can install this in your computer, and then you can feel like as if like how microprocessor executes this. You can do this with the help of this particular software. So then the syntaxes for this, and this I am going to cover in a special class with assembler directives, because in assembler, when you are writing your program in an assembler, then predefined instructions, like you are working on a byte or word, so db or dw or how exactly you mention. This is what we can try to see. Okay, all right. So then so we discussed like the addressing modes, we classified them based on the instructions which you are going to deal. 8086 has 105 instructions. All the instructions we are going to classify them as sequential control flow instructions or control and transfer instruction. Means after executing that particular instruction, the control will be going to somewhere in the memory location, not immediately. So then coming to the control transfer instructions, we can again classify these instructions as inter-segment instructions and intra-segment. Right, that means the control transfer is in the segment, means 64K, each segment is of 64K. Then one segment to another segment, the data is, means your control is transferring, or within the intra segment means within the segment, and inter segment means one segment to another segment, means beyond 64K. Based on these instructions, if you have inter segment instruction, if you consider, then inter segment direct addressing mode, the addressing mode related to this particular instructions, like inter-segment direct addressing mode, inter-segment indirect addressing mode. Examples. So coming to the inter-segment direct addressing mode, in this mode the address to which the control is to be transferred is in a different segment, but this addressing mode provides a means of branching from one code segment to the another code segment. Here don't get confused, like one segment, like a little bit here to discuss. All that means the memory, the processor which can access is of 1 megabyte. Right, this 1 megabyte memory is divided into small chunks, like 16 different parts. 1, 2, 3, like that. Each segment is of 64K. Then we have segments like code segment, data segment, right? Code segment, data segment, stack segment, extra segment. 4 segments only we are naming. But I'm saying you can divide this into 16 segments. Then how do you call the other segments too? That means you can have a code segment, that means the program which you are writing is beyond 64K. Then you can define the other segment as code segment. That means here 100, right? 1000 is one code segment, means 1002, 1FFF is 1FF. This is 64K. If your program is beyond, then what you can do, you can define 200 also a code segment which is of 64K again. Right? The meaning is that. Don't get confused. Then you can have a number of code segments and number of data segments or extra segments too. Alright, so the meaning is this. So this addressing mode provides a means of branching from one code segment to the another code segment. The meaning is this. Right? Here the CS and IP of the destination address are specified directly in the instruction. This is what inter-segment direct addressing mode. Example is this. You have call 200:0050. That means when we are writing program, we will write subroutines, because same task when you try to do, you will specify in terms of subroutine, and you need to call that. So then you can use this instruction call 200:0050. Your current segment, code segment could be 100, but you can call from the other segment, right? So where your subroutine is written in the other segment. So then you can go to that particular segment and you can execute that piece of code and then you can come back. Yes. So which is different segment. So this is one segment, this is the current segment. Right? This is an example of inter-segment direct addressing mode. Means you specify the address of the memory location of other segment in the instruction. That's why it is called inter-segment direct addressing mode. Then you have inter-segment indirect addressing mode. So in this mode, what you do is the address to which the control is to be transferred lies in a different segment, but and it is passed to the instruction indirectly. That is the contents of memory block containing 4 bytes like IP LSB, instruction pointer LSB, instruction pointer MSB, CS LSB and CS MSB sequentially. So the starting address of the memory block may be referred using any of the addressing mode except immediate addressing modes. So this is inter-segment indirect addressing mode. Then is intra-segment indirect addressing mode. So intra-segment direct addressing mode. So in this mode, the address to which the control is to be transferred lies in the same segment, right, in which the control transfer instruction lies and appears directly in the instruction as an immediate displacement value. So in this addressing mode, the displacement is computed relative to the content of the instruction pointer. So inter-segment indirect addressing mode. So now you can take this as an example. CS is 100. You have an instruction called the contents of DX. So that means your subroutine would be somewhere lying in the same segment. So then what you do is you can calculate your CS rate. Okay, your CS multiplied with an BX within the same segment, that is 1000, right? Or if the content, if you have any data, then DS multiplied with BX. Okay, so that content there, right, and that you can use to BXs. So this is what 10H multiplied with CS, and then that will be moved to BX. So now 10050. Your code segment is here, and then the effective address is also within the segment 10050H. This is intra-segment, right? Intra-segment indirect addressing mode. You are specifying that with the help of a register S. Right? So these are all addressing modes. Now I'll just recapitulate how we started. Yeah. So we have based on the instructions, and when we are trying to use that instruction, we are going to define different addressing modes for each instruction. So coming to the types of instructions, sequential control flow instructions and control transfer instructions. And based on the sequential control flow, you have immediate addressing mode, direct addressing mode, register addressing mode, register indirect addressing mode, based addressing mode, index addressing mode, base plus index addressing mode, register relative addressing mode, base relative plus index addressing mode is what we have seen. And coming to the control transfer instruction, the control transfer can be within the segment, which is called intra-segment, or out of the segment, which is called inter-segment. Then again, 4 addressing modes are related with this control transfer instructions. That is inter-segment direct or inter-segment indirect addressing mode, and intra-segment direct or intra-segment indirect addressing modes. Right. So these are about the addressing modes of 8086. So then we will try to see instruction set of 8086. Is it all right? Right. So we have seen, now we can start writing simpler programs by using, like knowing the instructions of 8086. So the moment I explain, I try to use this emulator. It is freely available in internet. You can download this emulator 8086 for your 64-bit or some kind of thing. So you can start writing your program here, and then we can go ahead. Yeah, the moment I'll be using these things. Now, coming to the instructions, the instruction format is opcode. This is an opcode, and the destination and the source operand is. We are going to use the program in assembly level language. So why assembly level language means, we'll see, and then what are the operands. So here, this is what your source operand, destination operand, and then this is what your opcode is. This is the syntax of your instruction for 8086. And coming to the types of operands, you have three basic types of operands. Immediate, right, a constrained integer of 18 or 16 or 32 bits. Value is encoded within the instruction. The register, the operand can be an immediate data, or the operand can be specified in a register, or the operand can be specified in a memory. So three types of syntaxes you can use, like you can specify your data immediately in the instruction, or you can use the register to hold the data or the operand, or you can specify your operand in a memory, and which is pointed out is what you can see as. And coming to the instructions, when you try to write this in an emulator, you can use this label instruction, and then use colon, and then you can write comment. So if you see an example, you have start move AX comma BX. So your program starts here, and the instruction is move AX comma BX, and the axis. So there is one-to-one relationship between assembly and machine language instruction. And so this is what assembly level language program is. So when you use this assembly level language program, so this is how you build your executable programs. Here you have a source file, and then you are going to give it to an assembler. The assembler can be of MASM, Microsoft Macro Assembler, or 8086 emulator you can use. Right. So this assembler, when it executes your instruction, it converts your assembly level language program into machine level language program in terms of object files, and then you can link it, and then the linker will link these things, and then you have an executable files. And this is what Microsoft Macro Assembler, and how you can debug, and why you use assembly level language programming means you have two benefits. It takes less memory, and within less time you can execute your instruction. You can write your programs in C also, but the size of the program will be larger and it takes longer time. So this is what the reason why we try to code it in assembly level language. And then one of the most beneficial use of assembly language programming is real-time applications. So real-time applications, the quicker action, the quickly you have to perform a particular task. So then your piece of code should be small. So for real-time applications, you use assembly level language program. And easier way, sometimes you can use cross compiler too. That means you can use high level language program and assembly level language program written in the same. Then you will be having a cross compiler. So assembly language not only good for controlling hardware devices, but also performing pure software operations. So searching through a large table of data for special string of characters, code translation from ASCII to EBCDIC codes, and table short routines, and then mathematical routines are easy. Assembly language program, it performs in real-time operations. High-level language used to write those parts that are not critical, time critical. So there you can use high-level language programs. And coming to the machine language program codes, here these Intel processors 8086, 80186, 286, 386 et al. Are called CISC processors, like complex instruction set computer. So that means the instruction is having variable format. So then you can see now here you have an opcode. This is how you specify opcode, then D, W, and then the mode, right? A register R by M, and low displacement data or high displacement data. More in detail, if you try to see, an instruction can be coded with 1 to 6 bytes, 8086 instructions. 1 to 16 byte, 1 byte instruction or 2 byte instruction or 3 byte instruction or something. So then we are going to see, we will see this in detail. And yeah, so how to code it and all, I'll come back. So now if you have an instruction of move bx comma si, then its machine code is calculated like this. You have an opcode, right, for adding, and destination D and W. So here D is your destination, an AL source operand, and how many bits? It is an 8-bit. D is destination and W is 8-bit or 16-bit. So now here if you try to see, add bx comma the contents of si, so it is on a 16-bit. So the moment it is 16-bit, you write 1. If it is 8-bit, 0. So if it is 8-bit, 0, and if it is 16-bit, then it can be of 1. And this is what your destination. So this is your destination, and W stands for, like it's a word operation or byte operation. And coming to the mode, this means which kind of register, means register mode, and which register is AL, or you have so many registers, right? So now if it is register is 000 means AL, then W is 0. Register is 000 means W is 1, that is AX, right? And then for AX, this R by M, we will use this, right? And R by M, and this is how it is calculated. Then the which kind of addressing mode you have. So effective address calculations, when you guys go for, so it is bx plus si means you will be using the mode 000, right? And if it is in a register content, then you can use this 0000. This is what decoding is. So this instruction you have, move bx comma si, and then the content of si. So here mod bx si means 00, right? So if it is, then it is 01 means with displacement, and with 10 means 8-bit displacement or 16-bit displacement. You can specify here. So then you can use this 00, or here you can use 11 when register is, right? When it is register in this field, you have an opcode. So here you have an opcode, and D speed is a destination operand. It's 8-bit or 16-bit. And coming to the mod, the operand is specified by using register or register with some displacement, is what you are going to mention here. Okay. And then coming to these two fields, register and then R by M. So register means 000. This is the code for accumulator. If it is in a register, then accumulator is 000, right? And then counter register, D register, it's R by M, then you can use these things and registers are. Okay, so this is what you are now the operand. See how nicely it can code. This is an opcode, then a destination field of 8-bit or 16-bit, then which kind of addressing mode means how the data operand is specified. Then coming to the mode, you have, if it is you are using 11 means registers, and if it is 00 means displacement kind of thing, index register addressing mode, and means, and then 01 and means 01 means base plus SI plus D8, and coming to the mode 10 means 16-bit displacement. So the displacement is of 8-bit, then use 01 in mode, and if it is 10 means 16-bit displacement, right? And then coming to the registers, so if the registers here, okay, the registers are by M, you can write it as 000. When you are using this is accumulator register or different registers, when you are using, then use these things. Okay, so now if you try to take an example, so 000 is what you are register, and then R by M is the destination. Source and destination is how you specify, right? Source register or some kind of thing. So example, you can try to take up this. So how to calculate the machine code for add bx comma si. So then here it is, and the opcode for adding, the opcode is this, and here it is an word operation, right? So the destination here, right, and then it is word operation, it is 1, then D is 1 means what? D is 1 means, destination, it is 0, AL source operand, or that means, source operand is of how much size. Source and destination operands is what you have to mention. So example, if you try to see move BL comma AL means the opcode for moving is this, right? And then B is 0 here, and W is 0, 8 bits here. So that's why, so this is 1 0 0 0 1 0, and then, right, so then these of 2-byte instruction 88C3. All right, so this is of 16-bit, so then the 2-byte instruction, then its equivalent machine code is 03. So this is 0 0 0, this is 4 bits, this is 4 bits, so this is 0, this is 3, and coming to the mode, it is index. So when it is index, right, so here you have 0 0, so this 0 0 is written in the next field, okay, and then the register which is used is, so here register source and destination 0 1 1. So now if you try to see 0 1 1, so the BX register, right, 0 1 1, right, BX register, so 0 1 1, and then your source operand to 1 0 0 0 R by M field. R by M field 1 0 0, if you try to see 1 0 0 is your SI, right? So source and destination, and how you can code is, when assembler is converting your assembly language program into machine level language program. So this is 0 0 0 1 4 bits here, so this is of 1, and this is of 8 plus 4, which is 12, 12 equivalent is C. So 0 3 1 C. So add bx comma si is a 16-byte it is a 2-byte instruction. It is a 2-byte instruction. Then when assembler executes this particular code, then it generates a machine level code like this 03, by which your microprocessor can understand. So we are going into deeply, don't worry, you can practice and then move AX comma SI, then different examples you can try for. Okay. Yeah, so then now coming to the immediate addressing mode, we have already seen. So now coming to the instruction sets, all 105 instructions we cannot by heart, or we cannot so the easy way is classifying the instructions into different types. So then coming to the instructions, you have instruction data transfer instructions and arithmetic instructions, bit manipulation instructions, string instructions, and program execution transfer. That means unconditional transfer, conditional transfer instructions, iteration control instructions, interrupt instructions, and process control instructions. All the 105 instructions which are there with 8086 can be classified to data transfer instructions, arithmetic instructions, bit manipulation instructions, string instructions, program execution transfer instructions. Right, program execution transfer means when processor executes and transfer, you can use jump instruction as an example of unconditional. We'll see one by one. Now, coming to addressing modes, yeah, this is what the summary of what we have done. So these are the addressing modes, okay, and example of those addressing modes. And now let us go ahead. This is what the flag register, already we discussed this. Okay, right. Yeah, coming to the data transfer instruction, move is one example of the instructions. Move. So mnemonic is move, meaning is moving something, moving data. So the format is move. What do you want to move? From source to destination. Okay, right. And so here the operation from source to destination you can move. When processor executes this particular instruction, no flags are going to be affected, right? So that coming to, we are going to see one by one what are the instruction comes under data transfer instructions. So the move. And coming to the destination and source, the destination can be a memory, source can be an accumulator. And destination can be accumulator, source can be memory. And the source and destination can be register, source and destinations can be registers, or you can move from register to memory or memory to register. And you can move from register, immediate data you can move into a register, or you can move an immediate data into a memory, right? This is how, when the moment you are writing an instruction, you have to follow these things. Okay, what could be destination, what could be source when you write a move instruction. But you cannot move, these are the special cases, you cannot move from memory to memory. So that means if you have something, two data, 2 bytes here, right? If you have 2 bytes here, you cannot move from this memory to this memory directly. So you cannot specify 2 memory locations in an instruction. So you can use this instruction like you cannot do this. Move 2 0 0 0 to 3 0 0 0. That means memory to memory you cannot move. So this way you should not write. Okay, and you cannot move immediate data to segment registers. See, you cannot write this move ds comma 1 0 0. No. So then how to move into ds register? Our segment registers, move through accumulator only you can move. Move ax comma 1 0 0 0. Then you can write move ds comma ax. This is the fourth step in writing your program. So you cannot move directly into the segment registers. You can move that through accumulator only. Whatever you want to move into DS, that means segment registers are not directly available for the user. And you cannot move segment register to segment registers. Right. So these are the cases you just keep in mind. And this is how you can use this particular instructions. Syntax example is move al comma bl is what you can write. Register to register you can move, right? But memory to memory you cannot move, and then these are some constraints. And coming, this is what the cases we have. Right, whether coming to the data instruction, this way you cannot write. Why? This is a memory. Okay, this is a memory, and this is also memory, which is pointed out by using source indexes. Okay. Right, this is also not correct because you are directly moving into the DS. This is wrong. Okay, now coming to this is one particular instruction, like move instruction, and then how to use this. So mnemonic is move, meaning is moving data or some kind of thing. So then the format syntax is move destination to source, right? So move some data from source to destination. So then your destination and sources can be this thing. And coming to when processor executes this instruction, move instruction, no flags are going to be affected. All right? Yeah. The next instruction is exchange instruction, XCHG. So what do you mean by this instruction XCHG? The mnemonic is XCHG. The meaning is exchange, and the format is you can exchange between a source and destination, right? Or you can, that means you can move from source to destination, or you can move destination to source. Then what could be destination and what could be sources? Your source, your destination can be an accumulator, and source can be any 16-bit register. So your accumulator, when you use an AX, then your source can be a register. Any register, you can exchange between any registers. Example, you can write instruction XCHG, the content of AX and the contents of BX. So when the processor executes this particular instruction, the contents of BX are going to be moved to AX, and the contents of AX are going to be moved into BXs. And when processor executes this instruction, so this is what for this particular case example. exchange instruction, how to use exchange instruction is what we are trying to see, right? So then the destination can be an accumulator, right? So you can write like this, or you can write like this: XCHG BX comma AX. So your destination here is AX. Source can be any register BX or CX or DX or whatever it is. So this is what an example. And you can exchange between register to memory. So that means you can write an instruction like this: XCHG. So destination can be memory, right? So your AX content is moved into a memory location 100H, which is calculated. The memory location can be calculated by using DS is multiplied with 16 plus this 1000 is going to be added. So that memory location content is moved into accumulator, and accumulator content will be moved to that particular memory location S. And you can exchange between register to register, any register to register, or accumulator to any register, or you can exchange between register to memory. The destination can be anything. Now coming to the example, exchange BX comma 1234. And this is the same example is what we have just seen. The content of BX will be moved to a memory location whose effective address can be calculated like this. So this is what exchange instruction is. Then the next instruction is special address transfer instructions. These are data transfer instructions here what we are discussing. Load effective address, right? LDS, LES. Load register and DS. The meaning is load effective address, load register and DS, load register and ES, load register and ES. Then the coming to the format is this syntax. You will be widely using LEA instruction, load effective address. When you are trying to do this, what do you mean by this? Load effective address into a 16-bit register. Okay, that means this instruction, example with example we can SI. See, operation is effective address can be a 16-bit register, and flags are not going to be affected. Example is LEA SI comma data. So that means yeah. Now you have an example, example of load effective address is this. See, load a 16-bit, that means the effective address, right? From a 16-bit, here what we can say, we can explain like this. Now something, I want to move into, like if I want to, you can take this as an example. Let us take, you have a data segment where your data is lying. So now this is data segment, and now you are writing your program, your instructions in code segment, right? You are writing your program in code segment. Now some data you have to copy, or some on these operands you have to work. So then what we do is we are going to point out this memory location by using SI, right? So then what we do, the program, this is what an objective, then what you write is, you can write move AX comma, that means, the data segment AX comma 1000, then move DS comma AX. That means you have to specify where is your data segment is. Okay. Then now you can say move BX comma contents of SI. Okay. So that means here move a SI comma 200. Move SI comma 2000. So that means you are going to move somewhere the data is there 12000. From that particular point, here now let us take this data segment is 1200. Then you have to write these many steps. But the moment you use this instruction, load effective address, then this effective address specified in terms of three steps. Instead you can use this LEA. That is the advantage of using LEA instruction. Then if you try to see the next instruction, LDS, the meaning of LDS instruction is load register and DS. So now you see LDS BX comma DI. What do you mean by this instruction? If BX is 127A and DI is 1000 and data segment is 3000, then and this is what 11100, the memory you are having some data. So then after execution of this instruction, the contents of DI with D, the contents of DI and DS going to be added, which specifies this particular address, right? And this is directly moved. This word is going to be moved in DS data segment, and BX is going to be moved with 12, right? Okay, this directly you can move this 12 into BX, right? And DS is going to be moved with this thing 00. This is an example. Okay, and now this is what this is how you can use LEA instruction. It's very important to know each and every instruction in detail. Now if you try to take this example, data X, that means you are having a data of 16-bit, you are defining that define word. These are called assembler directives. We can slowly learn these things, right? And now you have some X data which is at 1000 and Y data and at 500, and you are writing your program by mentioning it is a code segment. So dot code means from here you can start your code. Now LEA SI comma data X. That means when the processor is executing this instruction, then what is happening is what you can see, right? So load effective address into SI, then BXC LDS. In this particular instruction, then LEA SI LEA and LDS. So when processor executes this instruction, if BX is this, right, if BX is this, so then this register is going to be moved with 1 to, right, and then the effective address can be calculated by DI and SI. So DI and SI, if you add the contents, if it is 100 and then 00, right, so then this effective address, from this effective address, right, the contents are going to be moved here. DI and SI directly can be moved to 7A12, that memory location, right, and then the contents will be moved like this. This is LEA and LDA instructions. So these are data transfer instructions. So coming to the data transfer instructions which we have seen, move is one instruction, exchange one instruction, LEA one instruction, LDS is one instruction is. So these are data transfer group instructions, right? Then next we will try to see. Now see, slowly we are moving towards writing program, right? Okay, so then we have to know the instructions. So those instructions, just now we have seen data transfer, and similarly you can see arithmetic instructions too. So coming to the arithmetic instructions, so these are the arithmetic instructions. Add with carry, increment, ASCII adjust after addition, and decimal adjust after addition. So these are the arithmetic instructions, and I try to explain one, then rest of the instructions you can go ahead. The ADD instruction, when assembler encodes, and when it is, then the meaning is it has to add, then format is add source comma destination. Okay, source and destination can be added, and the result can be stored in destination after addition. And flags, all the flags are going to be affected by using this. So now let us try to see. An example. Move AX comma 1 2 3 4, add AX comma 2, and add C AX comma 2, right? So this example you can consider BCD addition and correction, add instruction. So you can add 1 2 3 4, right, 1 2 3 4. This small example you can take. I know how so 1 2 3 4 is moved into AX, and you are adding 2 with it. So here 2 means 16-bit is what you can write like this, right? So here source is a data, immediate data, and destination is in AX. So this immediate data is going to be added with, right? So here some immediately you are moving to AX, and then AX and 2 you are adding. So the result is 1 2 3 6 is going to be stored in accumulators. So the syntax is this: add source and destination, and the result will be stored in destinations, right? And coming to the thing, the flags, which flags are going to be affected here. Now you can check it out, your carry flag. So you know the meaning of carry flag. We explain very clearly. Carry or parity or sign and all, which flag is going to be affected, you can check it out. And coming to the ADC, with the carry it will add. Previous carry is there, that carry also can be considered here while addition. Right? So coming to the examples, so we can try to take each and every instruction and then we can go for this. Okay? So in the next class, I'll be dealing with this in detail. So one by one instruction, clearly the meanings and all, it is given in, okay, so it is given in the book. You just go through it, and few instructions, important instructions, I will be explaining in the next class with the help of simple programs, and I'll try to write the programs in the emulator by using those instructions to know clearly what the instructions are. So this will take 1 hour or our next period, so we can finish all instructions. Okay, right? So today we'll stop here, and then we'll be dealing in the next class. Okay? Thank you. Just go home, and today what we have discussed today is we have seen the addressing modes in detail, and all the addressing modes we covered. And then when you are trying to write your program, you are going to write in an assembler or an emulator. So then how assembler converts that particular assembly language program into machine level language program by seeing an example. We have covered that, and why we are writing our assembly language program is what we have clearly seen. So from now onwards, little bit, it is going to be difficult. Okay, because if you understand this, then only we can understand these days processes like your I3, I5 and all. So it is a must. Okay. So in the next class, we'll be dealing with different instructions by writing programs. Parallelly, I'll be writing programs in the emulator. Okay, and then we will be going there. Thank you.